So continuing with the alternating series and conditional convergence, let's do an example. We want to show that this function is decreasing, so usually just do f prime. So I carried out f prime, so check that out. Try that yourself. You want to show that f prime is less than 0 at some point. So if the denominator is always positive, we're looking for positive values, right, because you're approaching infinity. So x is going to be positive. So for what values of x is 2 minus x cubed less than 0? And we know that's true if x is greater than cube root of 2. You just solve for that. Thus, f is decreasing on that interval. So you get this statement, and a sub n is less than or equal to, a sub n plus 1 is less than or equal to a sub n. For all n greater than, now it's not going to be cube root. You just step up to the next integer, which will be, just pick 2. In that case, and so that satisfies the one of those conditions you have to have for decreasing. Then you take the limit. You want to basically verify that it does go to 0. So this goes to 0. You could multiply by 1 over n cubed if you wanted to, but you can see that this goes to 0. And that's those two conditions you need to have, that it's decreasing and that it's an alternating series and that it's the nth term approaches 0. So by the alternating series test, the series converges. Okay, so that's a pretty typical type of question right there. Let's go on to 10.7. This is on power series. So 10.7, let's first define a power series. So first, let x be a real number, and x is a variable. Okay, so x varies. And we say in this case, this is centered at 0. That's how we say it when it looks like this. So the power series written out would be this form. Okay, and then if you have it centered at c, then you say x minus c like that. So it's this form. All right, so let's take a look at an example. So find all values for x for which the series is absolutely convergent. And that statement really, you don't really want x to be alternating. That can get really weird and messy. So for now, we're just going to say absolutely convergent and see what happens. So there's a few ways to do it, and this is where you have to sometimes just try stuff. For now, let's go ahead and we'll let u sub n equal n over 5 to the n x to the n. And then we can rewrite that just for form-wise, n x to the n over 5 to the n. Okay, then, so now you want to find out what values of x will that converge. So you can apply all those tests we've had before. In this case, we're going to apply the ratio test. So then apply the ratio test. And you look at the limit, absolute value of u sub n plus 1 over u sub n as n approaches infinity. Okay, and I'm going to go ahead and move this so we have plenty of space over here. And so let's write that out. So that's limit as n approaches infinity, absolute value. And so we're going to be, we're going to be substituting in plus 1, and plus 1, and plus 1. And then this will remain the same. And we divide them. So we will invert and multiply. Save a couple steps there. So this will be all over. And then it's n plus 1, x to the n plus 1 over 5 to the n plus 1 times, and then flip it, right, because you're dividing by it, 5 to the n over nx to the n. and absolute values. And then we can continue to simplify. Remember, x to the n is x to the n x. 5 to the n is 5 to the n 5. Right, so it'll simplify quite a bit. So that equals the limit, absolute value of n plus 1 x over 5n. So if that's not obvious or simple, then check that out. Pause the video and do that on your own. So what we then have is this form. So remember that n is approaching infinity, so you don't really need those in absolute values. So you can say that this is equal to the limit as n approaches infinity of n plus 1 over n times the absolute value of x, because x is not changing. And so, oops, I forgot. Where's my 1/5? Okay, there's the 5. Should be a 5 over here. Okay, so that's equal to the limit as n approaches infinity. And then when you take that limit for n, what is this approach? So you can do this limit, that approaches 1/5. So you get, where did that go? So you get, actually that's kind of it. Don't need the limit there. So you get this is equal to 1/5 absolute value of x. So doing the ratio test, when does that converge? Right, so we'll look that up by the ratio test with, number has to converge to L, with L equal to 1/5 absolute value of x. The series is absolutely convergent if 1/5 absolute value of x is strictly less than 1, or absolute value of x is less than 5. So we know it's absolutely convergent if x is between 5 and -5. If it's equal to 1, the ratio test is inconclusive. So if x equals plus or minus 5, the ratio test is inconclusive. So you have to apply a different test. Okay, so we'll have to do that. So let's let x equal 5. Okay, then we get, where's our series there? All right, so we're looking at we'll just call it a sub n. So our a sub n is equal to n over 5 to the n x to the n. So our a sub n, if x is 5, would just be n, which of course diverges. It's just 1, 2, 3, 4, 5, etc. So and then the series a sub n diverges. By the nth term test. Okay, so then what if it's negative 5? So now let x equal negative 5. Then a sub n equals n over 5 to the n. And then it'd be negative 5 to the n. So probably best just to substitute in values now. So do a0. Okay, that's going to be 0. a1. Okay, so one way to do this is to bring out the negative ones. So it's negative 1 to the n times n. And then it's really just 5 to the n over n. So really you can see that it diverges. It's not going to converge. So it basically bounces between infinities, essentially, is what it's doing. Let's just leave it at that. You don't really need all this stuff. That's good enough. Okay, so it does not approach 0. Therefore, that particular one diverges by the nth term test. All right, so then what you get is the series converges only for x in the interval from negative 5 to 5, not including the endpoints, and diverges otherwise. So you say, and diverges otherwise. Negative 5 to 5 is called the interval of convergence. So it's called the interval of convergence. And then when you do x minus c, which in our case is x minus 0, which is absolute value of x less than 5, is called the radius of convergence. So 5 is called the radius of convergence. All right, so that we'll do more of that as we go, a couple more examples to hopefully make that a little more clear, but you're basically using one of the tests we just talked about to determine the convergence. So this is the ratio test, and you get the value L, and then what values of L, meaning what, so you know this converges if it's less than 1. So what values of X would make this less than 1? And that's how you determine your interval. Most cases, that's how you do it, similar. And then you got to figure out endpoints separately to test if it converges at the endpoints or not. This one did not, but others may converge on one and not the other. Sometimes it's alternating and it does work. So let me the left-hand side alternating will work, right-hand side maybe not. You have to test.